All right, welcome everyone to the Center for Acoustics and Vibration seminar. My name is Tyler Dare. I'm here representing the Structural Acoustics Technical Group. Today we have Dr. Roland Platz to give us a seminar. We don't have much in terms of announcements today. The workshop will be coming in October, but I don't think we have specific dates yet. And so look for more information on that as we get closer. So I will go ahead and introduce Dr. Roland Platz, is a research professor at Deggendorf Institute of Technology in Weissenberg in Bavaria. And he was recently a visiting scholar at Penn State for a year and a half, working on active vibration isolation with the Architectural Engineering Department. His research focuses on, among other things, active and adaptive state control and uncertainty quantification in structural dynamic systems. Today, Dr. Platz is going to be discussing a potential, I think, collaboration opportunity for quantifying uncertainty for passive and active vibration isolation. So with that, I'm pleased to introduce Dr. Roland Platz.
Thank you so much, Tyler, and jumping right into sharing my screen. If it's not visible, just say so, but I think we are all right. So I was given a similar talk 2 years ago at the CAV, seminar 2 years ago, also virtually. So some of you who did visit that 2 years ago, if you can remember that, some things may be similar, but the goal this time is different because, as Tyler said, I'm offering everyone a round-robin opportunity to work with me in collaboration and with others on that very problem. So just to give you a little heads up where I'm sitting right now, I'm 5 hours away from you. This doesn't. Okay, so I am in Bavaria right now and sitting in the Technology Center in Weissenberg, which is one of 13 technology centers the Deggendorf Institute of Technology is currently having. And it's a University of Applied Sciences. It's a little different system that we have in Germany compared to the regular universities in the US and the regular universities we have also here. And so the town I'm currently living is a small, cozy town, pretty much in the middle of nowhere and in nowhere of Bavaria. And close to Nuremberg, if some of you know where that is, about 1 hour south of it. It has a little nice marketplace. And if you love to eat meat and drink beer, that's the place for you. The Technology Center in Weissenberg, where I'm sitting in right now, is dealing with plastic material development and applications, and also motion dynamics, and that's where I'm working on. The motion dynamics, we have a rather big motion platform down here in the basement where we do structural durability and vibration tests. On the plastic side, we have manufacturing facilities for injection molding, 3D printing. We can do material testing and component testing, and also analytics. And the building I'm sitting in right now, and I'm right here, right now, it's a small building that we share with another University of Applied Sciences, and they do more the teaching, and we do more the technology work and the research. Model form in structural dynamics. This is one of the parts that I'd like to point out here. And for those of you who are not familiar with this notation, model form, and also uncertainty, it's a wide range. And there are lots of aspects to talk about, and it's hard to grasp sometimes. So I try to give you a little heads up and introduction into what model form and structural dynamic means, and also what we consider as uncertainty quantification and what actually is or what is uncertainty. So I don't have to tell you where to find structural dynamic systems. You're very much familiar with that. And before I joined the university here at Deggendorf Institute, I was, as Tyler said, first having my sabbatical at Penn State University in the architectural engineering department with Dr. Ses Atamturk-Tur. Unfortunately, after 6 months, I was, as you, witnessing the pandemic, so it slowed down a lot of things, of course. Before that, I was working and involved in a collaboration of the German counterpart of the NSF, the DFG, the Deutsche Forschungsgemeinschaft, German Research Foundation. And within that, I was working on problems in a big collaboration that was dealing with uncertainty in structures like that and structural dynamic systems. So we wanted to know about how loading and strength of a system may affect or may come out as an uncertainty measure in those systems. And we were building a system that looks a little bit and has the same performance requirements as a landing gear of an airplane. And we called that the modular active spring damper system. And this is how it worked. We had that in our lab, and we were just doing drop tests and see how the loading develops in that system. So we had different kinds of strut and strut elements. We had a spring damper system. We had joints, and all of that have their contribution to the dynamic behavior. And we were interested in looking at the uncertainty that arise in each development stage in the product development process, from the first idea to this strut or this spring damper system that you see here. Now, what model form can you actually use for that? Well, there are several options, as you of course know. If you have a structural dynamic system, you need to ask, or you need to answer the question, what kind of model am I going to derive for it to have the best representation of what is happening with the real system? Of course, we all know that all models are wrong, some are useful. That's the same as we have in here. For example, a multi-body representation of this system, or a finite element representation of the system. They all have their pros and cons. They're all not perfect. And due to the fact that there is imperfection, we would like to know to what degree this imperfection is going to show itself. And that's where we need to look at uncertainty and uncertainty quantification, especially model form uncertainty quantification. The ASME was giving out, and that's already also some time ago, in 2006, a kind of a review to go from a conceptual to a computational model, and is trying to give a guideline for verification and validation and computational solid mechanics. And we were using that also to have an approach for our structural dynamic systems. So what you see here is just a very generic and on a high level depicted graph from the conceptual model to the actual computational model, and what kind of steps you have to take in. And what you don't see here is actually that in every step that you see, there is uncertainty in every transition from one step to the next, from the concept to the mathematical model to the numerical algorithm to the coding, and so forth. And this brings us to this diagram where you see it a little bit in more detail, where you have the conceptual model, and then it splits into two branches. The one is the mathematical model, and the one is the physical modeling that you actually realize. And the mathematical model itself needs to have code verification in its different stages. The physical model needs that too, but the most critical part will be at the end, when we have a realized physical system that produces experimental outcomes versus the simulation outcomes of our mathematical model. And we compare that, and this is our validation. We then decide whether we agree with the outcomes or if we have to redesign or maybe have to do some changes in our system. Now, the crucial part here is this, where you have always a combination of data and model form uncertainty. And what is it? And why is it important? And why do we need to have a closer look, especially when it comes to its quantification in a consistent and comparable way, which is not every time the case today. So let me just talk a little bit about the terminology uncertainty itself. When I talk about uncertainty in structural dynamics, I mean basically two things. One is the model form uncertainty, and the other is the data uncertainty. Let's start with data uncertainty, which we all probably are more familiar with. It takes into account variability of parameter values, for example. So data, we consider data as being model parameters as well as state variables. Model parameters like stiffness, damping, inertia, state variables like speed, velocity, displacements, acceleration, etc. So these may vary, and we have possibilities to evaluate their variation. If we have enough data from experience, we can use measures from stochastic uncertainty, like if we know the distribution functions, as you can see here, we pretty much know a lot about the variability. This is not really called uncertainty, because when we have the data and if we have experience, we can pretty much work with it very reliable. It's different if we do not have distributions. If we go, for example, for membership functions, if you think of fuzzy logic, where we actually use just intervals and we don't really know how the distribution is, then we call that also incertitude, because we know a little less about our variation of our parameters. And if we just have one worst case scenario with a minimum and a maximum value, we don't know even, we are pretty much limited in what we actually know. And to deal with that, this is all called non-deterministic approaches, because we need to go to probabilistics or possibilistics. What we learn in school is rather deterministic. When we think of our first classes in technical mechanics, we were just using one crisp value for model parameters, and that's it. And then we were building up our models. So we were actually doing deterministic calculations. But we then completely disregarded any uncertainty. We didn't work with any density functions, with any intervals, so forth. So we were pretty much ignorant in this case. So this is about data uncertainty. On the other hand, you have model form uncertainty. What do we mean by that? You need to put the data that you get into some kind of functional relations, right? So whatever you have as data, you put them together, and this relation can be linear, nonlinear, it can be axiomatic or empiric. There are many ways to do that. If you are in the lucky position that you have a model that you can validate against experimental outcome, then you know pretty much about your limits of your model, but you are able to get a discrepancy term that shows you the difference between your model and the real world. And that would be, for example, delta. If you don't do that, if you don't do experiments and you just have the mathematical model, you can just assume that your model is right. So your ignorance increases until you actually come to the level where you have no idea at all how to put everything together. Now, we are trained engineers, and we have experience in getting the physics and empiric data together. So we always actually have an idea about how to model something. And this is also the problem, because we have lots of opportunities to model a structural dynamic system. If we talk, and this is primarily the focus, about model form uncertainty, we actually describe the imperfection of the mathematical model. This results into an unknown and incomplete or inadequate or unreasonable functional relation, and nothing will be perfect. We can also name that as lack of knowledge, when we don't know much about the relations, and the objects and processes that we are trying to model are completely unknown, unfamiliar, or even nameless to us. So this would be lack of knowledge. Disregard of knowledge is if we actually know that our system has a different behavior, but we ignore it. And as if you have a linear elastic spring behavior, for example, and if you just use that in the so-called linear range, then you're fine, even though you know if you have higher loading, for example, it's actually not linear anymore. And so you have a lot of approaches for uncertainty quantification that is within that model. And there are a variety of algorithms out there. So you can use deterministic or non-deterministic, probabilistic, non-probabilistic, parametric or non-parametric, unconditioned. That's when the frequentists come in, that they say that everything is on a random basis, or the Bayesians, they say that everything is actually conditioned and there's no such thing that pure random chance. So you have lots of possibilities to do your uncertainty quantification. And those are the challenges that we face today. From my personal point of view, and I've seen a lot of talks about uncertainty quantification. I've spent considerable time on going through literature, going through attending conferences about this topic. What I found after some years, that somehow this model form uncertainty quantification is pretty much stuck in academic efforts and frameworks. Algorithms become very comprehensive, very complicated, and the mathematical costs are getting really high. And the challenge to get to the idea behind each of these approaches is limited due to the lack of consistency and comparability in notation and application. For example, if you create your own application example, if you are in computational mechanics only and you don't have a real test rig, you just create your own so far realistic experiment, but it's never as I would say, messy as it can be when you do real experiments. What I've seen, for example, so far is they just put a little bit of noise into their model outcome and consider that as the experimental test. But it's not just noise, it's bias, it's all kinds of stuff that is going on there. So there's also limited feasibility and practicability to it. And most of all, and that reflects my time at the Fraunhofer Institute, very hard to communicate to industrial needs and use. If they see just one formula for one equation they don't understand, they said, no, thank you. We do as we do our business. And this is one of my aims as well, to do model form uncertainty quantification, not only for the sake of academic purpose, but also to have a benefit for industry, for the real world application. And that brings us to the round robin challenge that I would like to explain what I have in mind with that. The objective is that whatever structural dynamic system you have, you may create a very simple low fidelity model or a comprehensive high fidelity model. Both have their pros and cons. The simple low fidelity model is fast and easy to implement, but most of the times pretty much inadequate and contains a lot of uncertainty when it comes to validation. The comprehensive high fidelity model, on the other side, has very high costs to implement. It takes a long time to get to it. And but it may be more adequate with low uncertainty. But is this really the case? Are we able to decide in early stage design whether a model has a high uncertainty content or a low uncertainty content? Are we able to measure that and compare that? And to me, we don't have that yet. We don't have a metric that compares the uncertainty content. However, we will actually evaluate this content. If it's a vector, is it a matrix? Is it just one crisp value? I don't know, but it would be nice to have something like that so we can actually evaluate each model that we get with their uncertainty content, both model form uncertainty and data uncertainty, and to get to a comparable way to do that. And this is actually the basic goal of this round robin when it comes to uncertainty, model form uncertainty quantification in structural dynamic systems. And there is one reference system that I'm going to describe in a moment. So this reference structural dynamic model has to be, and that was the idea behind it, easy to understand. It has to be simple, but not too simple. We don't want to waste too much time in getting this system behavior tracked down and understand the physics behind it. It has to be pretty much obvious. It should be pure physics-based system that we can completely describe with physics, but also allowing phenomenological extension and improvements. Analytical relations should be there, but also discrete relations should be there, just for the sake of comparability of different models. So it has to be also modeled continuously, but extension has to be allowed to a high fidelity model. So allowing finite element modeling, multi-body modeling, substructuring, probabilistic surrogate models, etc. The team of Dr. Sess, for example, right now is working on the same reference model that we have been working for quite some time now, and is looking for the relation between goodness and of fit and generalizability of models and she's doing that with one of her current PhD students, Xingyu Zhu. And the good message here is there is experimental data, lots of experimental data for this very reference model that I'm going to describe right now. And for those of you who have visited my talk 2 years ago, maybe remember this picture. The motivation was to find a system that is easy to understand and it's easy to model, but also allows for more comprehensive modeling. So I simply took a car and a compression leg and model the dynamic behavior of that very compression leg in that car. So, and if you do it in the simplest possible way, you just have mass, damping, stiffness, and that's it. So, but that seemed to be a little boring in the beginning. So we thought we make the system also active, meaning that we add an active force into that, which will be realized by a velocity feedback control force to also allow better dynamic behavior. And this leads us to a vibration isolation problem that can be done both passive and active. So what do we mean by that? So if you have the passive configuration of this one mass oscillator, which is just is, and you add an actuator and energy into it and have it active, then you can overcome this well-known trade-off that in vibration isolation, if you have high damping going through the resonance, you lose this benefit in your isolation frequency range. And if you have very low damping, it's very bad going through the resonance, but it's very good going into the isolation region. And having this system active solves this trade-off because you can have great and high damping and also going through the resonance and also high damping being in the isolation region. And this you see in the curve of the amplitude frequency response with the thick lines. Those are the active cases, and the thin lines are the passive cases for different damping. And I was choosing one particular case that is in red, where you see that until you reach the resonance, it has the same dynamic behavior, but due to the fact that I'm going active, I have a much better behavior going into the isolation region. Now, how can I model this? This is the simplest way to model it, one mass oscillator. But also with this very simple model, you can ask yourself, do I only stay axiomatic? Do I just stay linear? Do I just stay time invariant? And I just stay with low fidelity in this model? Or do I allow to improve my model when I validate it to have empiric, have nonlinear, have time variant, have high fidelity issues here as well? So, and what we did so far is I was doing the investigations for model 1 so far for the one mass oscillator model. I was creating a 2 mass oscillator model of the same problem. We will see why the 2 mass oscillator model comes into place. And model 3 is a finite element representation of the very same thing. And there are numerous other models out there. And this is what I would like to ask maybe some of you who would work on a model that is modeling the same system, but in different ways, and then validate that against the very same experimental outcome. So we verified so far these very simple models. And when it comes to modeling validation, we were validating that with the experimental and realized system. And I will come to that realized system in a moment, because there's not that much to see right now, except that you obviously excite the system with a modal hammer. So for now, the takeaway is we have a realized system and we have experimental data to validate all different kinds of mathematical models. If you look at this table here, so far we have model 1, model 2, model 3, model n is yet to be defined within the round robin, for example. And you see different categories, what the model is standing for. Is it analytic, numeric, axiomatic, empiric, linear, nonlinear, and so forth and so forth. So if we look at the very simple model 1, we see that it's analytic, it's axiomatic. There's no discretization, there's no empiric data, there's no linearity, there's no time variance, there's no high fidelity. We did calculate an outcome, which is not that hard for a one-mass oscillator. So far, I was calculating the discrepancy between the model and the experimental output, but only deterministically. The uncertainty going probabilistically is still pending. We also did a 2-degree of freedom model, but it has the same criteria. It's also discrepancy and uncertainty still pending. The model, the finite element model 3, the discrepancy and uncertainty not even began yet. But as I said, there are more models to come, and they all have to validate themselves to the realized system. So this is just another wrap up, what we want to do with the round robin. I just skipped that. So for the last 5 minutes, I hope I still have 5 minutes. I'd like to show you on ongoing and so far investigations on this very most simple model form that we were using. So you have the one mass oscillator. It is analytic, axiomatic, linear, time invariant, has low fidelity, just uses physics, and it's continuous. The equilibrium of forces is there. You have the excitation. In this case, it's a base point displacement excitation for this vibration isolation dynamic outcome. And then what you see here is just the mathematical model. The differential equation of motion with some abbreviations you are all familiar with. And when it comes to the vibration isolation, this is what you normally get. The first diagram shows you the excitation, which is just a step excitation from this base point excitation. And the other 3 diagrams below that show you the displacement, the velocity, and the acceleration outcome of that very mass. So this is in time domain. And if you go into frequency domain, you just calculate the magnifying function, which is the relation between the mass acceleration and the base point excitation. And you get to this expression. So on the top, on the upper diagram, you see the phase difference, and down the amplitude frequency response. And now we need to validate that against some. So how did we realize that experimentally? And it turned out it wasn't that easy just to have a one mass oscillator subject to vibration isolation to be transformed into an experimental setup. So we did some tries, and so then we came up with the idea that we actually put this one mass oscillator into a frame. This frame does have a mass. This frame is mass is MF for frame. And of course, this frame also needs to be referenced somewhere, fixed somewhere, and it's fixed by a very low damping and a very low stiffness. And when we just take this system, and this is the lower right diagram, this is how we realize that. So you see the mass in the middle, the oscillating mass in the middle, within a frame, and it is supported by leaf springs, where you can change the length of the springs to change the stiffnesses. And there's a modal hammer that is giving us the excitation. I actually wanted to have a shaker, but I didn't have the money to do that. And when I went to your university in State College, it would have been too heavy to carry on. So I decided to just use a modal hammer for that, and that was doing the same good work. So the hammer is giving us the impulse force excitation, and from the impulse force excitation, you can recalculate the base point displacement, and having the same experimental impulse as your input as a base point displacement in your one mass oscillator. So you're all good and can directly compare these different outcomes from the simulation of a one mass oscillator and the experimental setup. And this is how it looks like. This picture is taken from the architectural engineering department at Penn State. I took this whole system with me, and it's now back here in Bavaria. I bought it from the University of Darmstadt, and now I have it here, and I can continue the experiments with that. So the one mass oscillator is actually within this construct here. It is not easy, and I try to get a decent photo, but it's not that easy to get. So let me go through the different components, how we realize the oscillating mass with the cantilever leaf springs. So you see the mass M in the middle, and then we just had a support design for the leaf springs that we can change the length of. And for damping, which is always the critical part, we used a simple voice coil actuator that we used for the passive damping and for the active damping. And it creates an active as well as damping force. And we had here a D-space system, a real-time controller that is giving us the controlled damping forces in case that we have pure passive damping or pure active damping. And that worked actually very fine. And this is how we realized the inertia, the stiffness, and the passive and active damping with the voice coil actuator. And here you see that changing the inertia was simply done by magnets that we put on the original mass. So we are able to vary the mass of the system. We are also able to vary the experimental damping output by using the voice coil actuator and taking into account the electromechanical circuit. And down here, you see that we created a voltage model that is directly linked to the mechanical damping, whether it is passive damping or active damping. So knowing the electric voltage here multiplied by the current and the velocity, we have the equivalent to the damping forces that we actually use in the one mass oscillator again. So we were all good, and this one corresponded pretty well. And for the leaf springs, as I said, we are able to adjust the mass. Now, what kind of data is available? Also, the data I would like to share with everyone who is joining the round robin is when you look at the design of experiments. I was creating 3 different scenarios for stiffness, for mass, and for damping. So all in all, I was creating 3 different stiffness cases, 3 different mass cases, and 3 different damping cases for passive and three damping cases for active. Gives me this design of experiment procedure here, that for each stiffness that I take and for each different mass I take, I use different damping. And that took a while to get all the experiments done with the also the frequency resolution that I wanted to have. So it turned out that I have to hit the system and wait for 12 seconds to get a decent frequency resolution. And I was also averaging each excitation. So I was hammering 5 times to get one averaged response out of it. And this is how it looks like in time domain. If you look at the numerical simulation on the left side and the experimental test on the right side, you see already some discrepancies, but we haven't quantified them yet. And also in frequency domain, you see here that for one particular case, for one particular mass and stiffness, but with varying damping, you see on the left side the numerical simulation results and on the right side the experimental results. And if you look at the original data that I'm going to share with you, if you like, it looks like this. So I have data for the excitation force, data for the damping force, for the combined damping force, which is just going through the voice cord actuator, and then, which is probably a little bit hard to see, accelerations for the oscillating mass and the frame mass, and also the from then calculated velocity values from the oscillating mass and the frame mass. And if you look at the experimental output for the same stiffness, but with varying mass, you see this, pretty much what you expect. So with higher mass, you have a frequency shift to the left. And down here, you also see for control reasons the coherence function. And within the range, what is most interesting for us, it seems to be okay. Now, the first look into the discrepancy when we have a passive vibration isolation case and we compare the numerical output with the experimental output. And I was just doing a deterministic least square fit of the parameters that you see here. And I was using control parameters that I pretty much know how to handle. That is the frequency and the mass, which is easy to weight. And calibration parameters were just the stiffness and the damping. So I was kind of a model updating. And you see here for 3 different cases, like this is the case for the lowest this was for the lowest damping. This was for the medium damping, and this was for the highest damping. The phase shift, the amplitude, the amplitude frequency response, and the coherence function. And you see the higher the damping, the worse actually the, or the higher the discrepancy. Whereas if you have very low damping, then you have very good or very similar simulated and experimental results. So first takeaway, this model is not good for higher damping. The discrepancy in higher damping is getting higher for the passive case. Not so much for the active case, where we are able to get an additional active force into the system. Then we see that also at higher damping, our discrepancy is a little less. But I was not doing any probabilistic evaluation yet. This is all deterministic. And so at the end, what I want to have is, according to Kennedy and O'Hagan and Hitchton approach, to describe the experimental outcome with what you are simulating here. So this is the simulated model, this is your discrepancy function, and this is your experimental measurement error, which is in most cases just noise. But it isn't just only noise. It also contains, and this is brought in from me, some kind of a vector that considers all kinds of measurement uncertainty and also the bias that you will get. And in this particular case, noise is not that much of an issue. It's the bias, and it's the wrong physics that I obviously use in this very simple one-mass oscillator model for the damping. So to make a shortcut, I know I'm running out of time, so just give me one more minute and then I'm done. So I was looking into measurement uncertainty. I was looking into the measurement uncertainty for experimental damping. And I saw that if I measure the damping in different ways, like using the logarithmic decrement in time domain or the half power bandwidth in frequency domain, and use also symmetry assumptions, then I get different results for my damping. So what is my correct damping? I don't know. I have tried quite a bit and with different approaches, and you always get different results, but that's damping. So I saw that there is up to a 8.8% deviation from damping in this case. What about reproducibility of the stiffness? So I was mounting and demounting the whole test rig and trying to get a force displacement diagram to see how the damping is evolving. And we also see that you cannot reproduce the damping, the stiffness in a proper way that you have zero uncertainties. Just no way to do that. So this is what it comes, even though if you try your best and get it all laid out nicely. And also here, if you see the box plots, you have quite a lot of differences, up to 6% differences in damping. So let me just go directly to the conclusion and outlook. First of all, what this example shows you is one side effect, that the active approach is doing what it's supposed to do. It enhances the vibration isolation behavior. There is data uncertainty. I checked that. So it is all within the margins that the manufacturers are giving us when it comes to the sensors and the sensibility of sensors. Model form uncertainty, so far I was just using a least squares minimization, and doing that I noted a poor prediction quality when it comes to high damping, especially when it's passive damping. So obviously this model is too simple, it's incomplete, and it's insufficient, and it's inadequate for getting validated. So this gives me the reason to look at other models, but I don't have the strength to do it all by myself. So I'm looking for help to do a joint collaboration in a round robin. And when I was at IMAC conference last month in Austin, I was also offering those attendances over there this concept of the round robin. And we will have a special session in the next year and in the following year about this very problem. And everyone who is interested in working on that problem, meaning that finding different models and finding different uncertainty quantification measures, is welcome to join. And I will have a virtual kickoff meeting next month. And if you're interested in learning more about the round robin and learning more about how to contribute, you're welcome to join. So just contact me for the round robin. And it was my pleasure to talk to you. And I also like, of course, to thank the German Research Foundation to make that research possible so far. Thank you.
Great. Thanks a lot. Thanks a lot, Dr. Platz. That was really quite interesting. We do have a handful of minutes for questions. If there's any questions from the audience, maybe while they're thinking of their own questions, I can ask one. I mean, I think this is a really interesting thing. I think a lot of us are sort of familiar with, oh, if there's some uncertainty in the spring stiffness or some uncertainty in the mass, this is something we teach to the undergraduates, how to propagate that uncertainty through the equations. But I'm not sure I've heard a lot about the uncertainty of the model form. Can you maybe give us an example or something, like say we had, how can I tell if I need to model a spring as nonlinear, for example, based on some data? What are some things I should be looking for?
To prove that it's actually a nonlinear behavior?
Right.
Well, in this case, I would just do a very simple experiment and having different weights and different loads on that leaf springs and see what the displacements are. And if this has a linear behavior, you have to do it static.
Static, okay.
It has to be static, yeah. If you try to do it dynamically, it's not going to work. It has to be static. And this involves more work, of course, but if you really want to get to the roots of it, you need to do that static. Okay,
interesting.
And that's what I did. That's what I did.
Yeah. Any questions from the audience? I think some people have had to sort of jump off here. If you send us the details about the kickoff meeting, we can share that with the rest of the CAV group.
Yeah, that would be great. I didn't expect that everyone says me.
Sure.
Yeah, we can do that. I will also send you just the presentation.
Yeah.
I will convert that into a PDF, and then you have and everyone who is interested, just think about that. And I'm happy to receive maybe some questions from the audience. And I haven't set up a date yet for this virtual meeting. I'm still working on it, and I probably have that done maybe in the next 1 or 2 weeks.
That sounds great. Well, thank you, Dr. Platz, and thank everybody for joining us, and we'll see you on the next CAV seminar.
Thank you. Thank you for having me. Bye-bye.
Diane, can you stop?